Next is diving a little bit deeper and understanding that everything must have a tolerance. Everything. You need a limit on anything that you put on a print. But you want to give production or quality or anyone that's producing your parts as much room as possible. So let's first discuss tolerances and perfect parts, the CAD parts that we usually make. They don't exist in real life. Your CAD model will never physically exist in its perfect shape. It'll always be off by a couple microns here, maybe, or a few thousandths here. Consider how parts are made. No part will be ever perfect. A part may look nice and smooth. You may have a part here like this, which looks very smooth. But if you dive down into the surface, you have these imperfections. And those of you in kind of the high precision areas, biomed, high technology, automotive, aerospace, know that this can make or break an entire system in your assembly, is having variation along surfaces and things like that. So perfect parts are also unattainable due to things like tool usage, right? When you give something to a supplier, their tools are going to wear over time. They're not going to make it with a new tool every single time that you have it. You'll also have machining errors, programming errors, material stresses, inspection methods. I mean, sometimes your part's made really well, and sometimes the inspection method you can't get to that to inspect it. So there's an issue. The employee skill level, environmental conditions, you name it. It is impossible to always make your perfect part. The higher the volume too, the less likely you're going to have it. So how do we define what level of imperfection is acceptable? Well, that's where we get into tolerances. And really what a tolerance is the acceptable range of dimensional variation that still allows for proper function. If design wasn't hard enough to make sure that the thing doesn't explode or break when you put stresses on it, you also have to make sure that if they screw it up, how far can they screw it up before it's still, or to make it still properly function, right? You need to allow that amount of variation. So this variation defines the maximum minimum limits for any dimension, whether it be geometric, size, it could be spring force, right? You have a tolerance on that. So here's an example here. We know the diameter of the shaft isn't perfect. We can apply a tolerance to control a diameter while ensuring proper function. So in our 3D model, we might say that this is, and this is an inch model here, that it's 3.858 inches. But it's not going to be made that way all the time. Is this a critical journal surface that's rotating at 10,000 RPMs? Or is it just a boss that something's going to get hooked on? I don't know that by looking at the nominal dimension. I need some sort of tolerance. So we need to know what is acceptable with that. And that's why we've developed a geometric dimensioning and tolerancing system. And this is just a simple plus minus tolerancing that we have here. Basically what we're saying is, in a perfect world, we'd be at 3.585, but we can vary by 5 thousandths or 0.005 inches from that nominal. And by the way, these other ones that I have listed here, they're just different ways of saying this thing right here. We know the diameter of the shaft isn't perfect, so we're giving some sort of limitations. But honestly, all 4 of these things right here mean the exact same thing. There is no difference. Sometimes companies specify, not to get off on too much of a tangent here, but sometimes companies specify that you have to do limit dimensions like this so that you know the absolute limits for inspection. Some, which are especially production facilities and machinists, love when you put it in plus or minus something, right dead nominal, because a machinist is going to be targeting 3.585 every single time. And they're going to hope that they get it dead on as close as they can. And then you have other variations that your company may or may not use. Some are due to statistical tolerance control. Some are due to single side limits, which are another reason people put these types of tolerances on. So there's multiple different ways, though, of showing tolerances on a print. But all dimensions, anything geometric, anything size, location, orientation, or form must have some sort of limit. It can be a general limit on your part, like all diameters are plus or minus 10 thousandths. Perfect. That's done. That's covered. But you need to have some sort of requirement there, because we have to be able to communicate manufacturing limits. right? In this case, we have a 0.5 total length tolerance, which is plus or minus 0.25, on a part that is 20 inches long. We can clearly see that the target is 20 inches, and where are the limits? Now, if I'm making this part, I need to know that. And keep in mind that sometimes it's good to put dimensions on the print like this, like a loose 1/4 inch tolerance, plus or minus 1/4 inch, because you're letting them know that, hey, we can vary a little bit more. That's okay. Make this really quickly, make a quick cut here as opposed to something else. So again, there's multiple reasons that you have it. The big reason that people cite is that it helps convey critical dimensions. And that is absolutely true. When you have a critical dimension, let's consider this pocketed feature right here. Without a tolerance, we have no idea how important this dimension is. If I sent this to my supplier and said, hey, do the best you can, they don't know if they have to do, precision boring. They don't know if they have to, or if they can just use a hand drill and drill this into there, right? Can we drill it by hand? Does it need to be reamed? With this type of tolerance, we can guess that it serves a critical function. I have plus 6/10, plus 2/10 here. That is a very important part right there. A very important feature on that part right there. So we now know that in production and in quality that, hey, something's going on there. I usually tell production facilities, because they usually give me big kickback on GD&T a lot of times, that you shouldn't be afraid of symbols, because symbols and things are just other ways of displaying things. But you should be afraid of small numbers. And small numbers mean that this part is going to cost quite a bit of money to produce, because they're going to have to be very careful with that. And this is even ignoring the effects of location on this hole as well, how centrally located that hole is. So, perhaps the other thing that designers often miss, and I've seen this at a lot of facilities, is fit and function, assembly, right? We're designing for manufacturability. We want two parts to go together every time. If I have these two parts and I just send it to manufacturing, well, sometimes the part on the left, the boss, will come in a little big, and sometimes that feature with the hole will come in a little small, and guess what? They're not going to fit together. And we have to account for tolerance stacks, which is what this is called, and tolerance variation that will result in this. So that's why tolerances are so important for production. We're trying to have accurate communication on what processes and inspection methods we're going to be doing. We need to know how important this is to be able to give it that justification, and to make sure our inspection methods are catching this type of thing, and how often we have to inspect it, perhaps. And finally, we want to make sure that things fit together and function in assembly. And by the way, I'm starting to see a couple questions come up here. Thank you. Keep the questions coming in. That's perfectly fine. I'm going to address them at the very end of the presentation. I'm saving about 15 minutes here just to go over any questions you have. So feel free to add them right now. I'll get to them when I'm completed with this. Thanks. One thing that I did forget to say too, from a legal standpoint too, all designers, and this is something that you don't realize until you really get into the high volume world, they define the acceptance criteria for part inspection when we get to tolerances. If you're dealing with a supplier and they send you a bad part, you have a legal document. That's your drawing that says that you can't send me that, and that I am not accepting that as scrap. There is millions and probably billions of dollars that goes into part lawsuits on things like this, all because of proper communication and making sure that your drawing is extra clear on what those limits are. So just be aware of that. Again, just an example here, tolerances don't have to be dimensional. You have your, main dimensional tolerances, sizes, orientations, location, form, GD&T, orientation here that we have perpendicularity callouts. You could also have forces and loads here. We have a spring rate on this. That is a requirement, right? It's a testing criteria, but it's really not dimensional. And then you have other tests. You have certain tests. You might have like a Rockwell or Bernal hardness test that you have to do on the material, a material qualification. You may have weld inspection, other things like that. Tolerances don't necessarily have to be dimensional either. Okay, so let's show now, dive in a little bit more on the GD&T framework that we have. Rules that apply to every tolerance. So really our framework that we teach here at GD&T Basics and Engineer Essentials is this, and we try to simplify it as much as possible. I'm trying to explain GD&T in probably 5 minutes here. So GD&T in a nutshell is really how are we going to be controlling geometry and dimensional tolerances on our print. And there's a couple of rules that we have to follow. The first rule is everything on a print is what is required for function. The reason you put something on a print is to design it because that is what you need for the part to do what you want it to do. Whether it means that it won't break in half, whether it means it'll rotate at a certain speed, whether it means the part will have certain performance goals, it assembles, could be a basic thing. Everything we put on a print, the reason for it is about function. And you shouldn't put things on prints as a designer. You shouldn't put things on prints on your own to tell someone how to make a part. You leave that up to manufacturing. You leave that up to the supplier. Now, a supplier can give you feedback to tell you, hey, we'd like this on the print or things like that. But when you're first designing a part, you're thinking about how will this part work? Function first. Then, only then do you think about design for manufacturability, inspectability, and other things that maybe your suppliers or your manufacturing department will want on there. But it always comes function first. The other thing about GD&T, and this is a quick shortcut to all the symbols that are out there, everything is a tolerance. We call it our tolerance from target guideline. Everything is toleranced from perfect. Meaning, if you have, let's say, a flatness tolerance, perfect example. Or actually, let me talk about a circularity tolerance. That's even easier. A circularity tolerance. Well, what is the target of circularity, do you think? Well, it's making something a perfect circle, right? So the target that we're aiming for is a perfect circle when we're putting a circularity tolerance on something. Now, what we're giving, though, the tolerance is how far from a perfect circle can we actually be with this feature that we have. Position is another one that I'm sure most of you have on your print somewhere. Some of you call it true position. The tolerancing symbol is called position. But we have what's called the true position, which is if we made this part exactly perfect, where would this hole be located on the part? That is the target, right? And then the position tolerance, the number in the frame that we put in there, is how far from that perfect target are we allowing for production. And that's all it is. That's all of the tolerances are all, where are we aiming for in a perfect world? Basically our CAD model, right? Where is it on our CAD model? And then how far from our CAD model can this actually be? There are only 4 ways, as I said, of how you can control anything geometrically on your part. You have your size, how big is the thing? So if I'm putting a hole on a part somewhere, right? Well, how big is that hole? What's the diameter? Simple as that. And then how big or small can it be? As a drill wears out over time, that hole is going to slowly get smaller, right? So when does I have to tell them the requirements of that size tolerance? Because over time, they're going to be trying to hit that target, and it's going to be kind of a moving target for them. So I need to say what is acceptable when you hand me the part at the end of the day. Location. This is something that a lot of people miss because that hole has a size, right? We also need to know where is it relative to the rest of the features. A lot of you are aware of the term datums, right? And sometimes we have datums on parts. Well, all location is how far from our datums, or exactly where from our datums should this be? And then what's the tolerance from that perfect location? So that is location tolerances. Orientation, you can think of it the same thing kind of as location, except now it's like, well, I want this perfectly at a 90-degree angle, but I'm going to allow it this far from 90 degrees in any direction. And then I'm giving that tolerance on there. Some of you may see plus or minus angle tolerances. Very commonly, and what we push for are things like perpendicularity, parallelism, angularity on prints. They're much more clear. And then finally, we have form. Flatness. A lot of people see flatness on a drawing. Well, what's the perfect version of that? Well, in a perfect world, it'd be a perfect plane, right? Well, how much variation from a perfect plane, essentially how wavy can my part be from that perfect plane that we have? A couple more things before I move on here is Size in GD&T controls form. I don't have much time to get into that right now, but when you put a size tolerance on there, you're also dictating how much form requirement there is due to a rule called rule number 1 in the ASME standards for GD&T. And then we have location typically is going to be controlling orientation too. So if you have if you have position tolerance on a hole, giving it a location, and it's to a datum that's maybe on the bottom side, it's also controlling the perpendicularity as well. So these are not only, just 4 symbols, but most of the time you're only considering size and location because there's a hierarchical system where location will already cover orientation. The other thing about our chart, the reason we drew it this way is size and form has nothing to do with datums or other features on the part, and location and orientation exclusively deals with where and how it's oriented to other features on the part. And that's why we drew our framework this way. So again, this is my little GD&T spiel in 5 minutes of how the basics of a 350-page standard, how it all boils down to kind of simply here. So let's get into just kind of a very basic example of this tolerancing framework. Let's get into just one feature here, this clevis hole. When we are designing a part, we have to consider a lot of these questions here. And remember, I talked about size, location, orientation, and form. All 4 of those things need some sort of tolerance. A lot of them come from either our title block, default stuff, or they're inherently built into other symbols that we're including. But we still are considering, what is the size tolerance on this hole? Well, it can be between 1.125 and 1.135. That's it. If it's anywhere outside of that, part's rejected. It won't function. What is the target hole location on this part? Well, we have some basic dimensions here, but you can see this is a datum right here, this A. And we're saying that this is exactly, I think this is an inch drawing, so this would be exactly 2 inches from the bottom surface of that part. And we probably also have another datum here, this 2.5625, which is on another view. But we're giving basically the perfect location in 3D space of where that hole needs to be. That's the perfect target. But then we're saying, okay, from that perfect target, basically from where it should be in the CAD model, you can be 1,000th off, and that's 1,000th in diameter. So you can actually only be 0.5 in any direction. But you have a total variation of 1,000th, basically 0.0005 up, down, left, right, at any angle in any direction. But geometric tolerances are always total tolerances, so they're always specified as a diameter, not a radius, just so that you're aware. Again, how far of an angle can they be within that location? Well, because we don't have any other refinements on here, this position tolerance is actually, if there was a datum kind of basically on the same plane as your screen right now, if one of these datums was on there, well, we're holding perpendicularity to that datum as well, because it's built into that position tolerance. And how round do the holes have to be? If I wanted it to be maybe a very precision bearing surface, I might need to specify a type of circularity because it's a raceway surface for bearings. We can't have any waviness along that. So if I wanted to specify that, I'd had to, but due to some of the rules in GD&T, one of the rules, rule number 1, it is actually built, the circularity is built into the size tolerance as well. So as you can see, one simple dimension on here really has 4 controls that I'm giving it. A lot of them, I'm really only giving it a size and a location. And then by default, the form and the orientation are built into it. But I do have to consider that. It's hard. After all, when you're designing this part, you're probably trying to make sure that it functions, and during the stress and strain that is on it, that the part doesn't yield or bend or anything like that. And then you have to come in though, and you have to make these considerations as well, because this is all about function. If I don't hit this 0.001 in position with this, the pin that goes between there might be offset enough where I get a bending moment on my piston and it snaps off after 1,000 uses, right? So there's so many considerations that we have to make as designers, and we have to communicate that information. So once again, I'm just quickly go through this. How do we specify tolerances? This is the biggest question we get. I do want to spend a little bit of time on here, but I'm getting behind a little bit on time. there's several ways which tolerances can be determined. We have existing parts, engineering knowledge references, scientific principles, and professional experience, which is a big one. That's why for those of you looking for engineering jobs, or those experienced looking for engineering jobs, that plus 5 years experience is always on there. This plays a lot in design, unfortunately. It just happens to be the way. Professional experience is one of the best ways of understanding how much tolerance to give something. However, what can you control, right? Existing parts are always one of the big ones. If you're at a company and you're trying to understand what tolerance to give something, take a look at what tolerance was given in the past, because typically it's based on function and manufacturability, because you have to balance that between how well the part functions and can we actually make it. Engineering knowledge references. For those designers out there who are putting any tolerance on a print, if you do not have a machinist handbook, they're called a machinery's handbook, go get one today. They are, a couple things. If a production or quality person thinks that you're pulling numbers out of your head, this is basically where you can prove certain tolerances and manufacturing limits come from. It's the answer key to many tolerancing questions out there. Every designer working with parts that I mentioned at the beginning of this should have one of these on their desk. It's used all the time, especially if you're applying direct tolerances. Also, you'll get a lot of respect from your machinists and your quality department if they do see that and that you're actually using it, because these are the tried and tested practices from probably over almost a century of doing machining and engineering work. And then finally, scientific principle, studies, research, reports. You might be testing tolerances. That's its whole other thing. Your R&D, your testing departments, that sort of thing will dictate your tolerances. And the big one that we don't mention right here is talk to your machinist, talk to your manufacturer, talk to your supplier. When you put something on there, don't just assume they understand what it means. Talk to them and ask them, like, do you understand that this is a tight tolerance because of this? You need to be able to produce it. If you don't, quote unquote, don't care about something, it still needs a tolerance, but that tolerance should show that you don't care. Give it plus or minus a quarter inch if you don't care. Perfect. That tells me I can hand drill it if I need to. Again, realistic tolerances, tolerances on the print are limit what function will allow. Just remember, the tighter the tolerance you're giving, the more expensive the part, the more your machinist and quality department will dislike you and will question everything you're doing. So be very careful of putting these extremely tight tolerances. Also, one piece of advice for all of you designers: if you hand a drawing to production and everything is plus or minus 10 thou, they are not going to take you seriously, even if that is truly what the tolerances are. You should be explaining things. There should probably be some variation on your tolerances because you're functionally showing what is important on your prints. Again, one quick thing here that I wanted to get into to make sure that you don't sound like a newbie when you're talking tolerances, especially with production and quality, is the shop talk, let's call it. For those of you who are not aware, the word thou or thousandth or mil, all of those mean 0.001 inches. Someone says that's a thousandth. They don't mean a thousandth of a millimeter. They don't mean a thousandth of some other unit. They mean a thousandth of an inch. That is called a thousandth, right? A mil is not a millimeter. I made this mistake very early in my career, saying, oh, it's 15 mils. That's a lot bigger than 15 millimeters is a lot bigger than 0.015 inches. And that is what a mil is in the standards. If you see anyone using mil and millimeter interchangeably, they're incorrect, and you might want to nicely correct them. Going smaller, now we have tenths. And by the way, I'm right on like inch right now because inch has a lot more shop talk rules. I actually grew up I learned metric most of the time, which is way easier. But common terminology, this is a tenth, 0.0001. I've made this mistake before as well, where someone said, oh, it's, I need a tenth of tolerance there. I'm like, you need 0.1 inches? I can't give you 0.1 inches. No, they mean that they need a tenth of a thousandth is what a tenth means when they say this is a tenth off. So going into metric, very easy, microns. If you're dealing with tight tolerances and things like that, you have millimeters when it's bigger than a millimeter, but you have microns when it's under a millimeter. Even when it's 0.2 millimeters, it's usually better to say 200 microns because we're usually dealing with that level, especially if you're in the automotive, aerospace, biomed, those type of tolerance places. So again, just really quickly through here, some shop talk. 5/10 is 0.005, 0005. 200 thou, 0.200. And then 50 microns. It's common tolerance is 0.05 millimeters. So just be aware that these are probably these are the three biggest ones: thousandth, tenth for inches, and then microns, if you want to sound like you know what you're talking about.